You're watching MyIPS on MyINDY-TV 23, a free educational service provided by Circle City Broadcasting of Indianapolis. Here's what's coming up this hour. Get more information, special announcements, and weekly program schedules online at wishtv.com. And be sure to follow us on Facebook. Here's what's coming up next.
Hey, fourth graders, welcome back. This is Mr. Nick. We're ready for fourth grade mathematics, week 3, day number 1. Your first activity for today, it's asking you to make, using it almost looks like a geoboard, is connect some dots together to create different geometric figures. So two-dimensional figures in this case, and I'm going to give you a little secret. The very first one, it says make parallel lines. If we end at the dots, those aren't going to be lines, those are going to be line segments. So you might want to talk to your teacher about that if you play online this week. So parallel lines, perpendicular lines, right angles, obtuse angles, and acute angles. So I'm going to start with parallel lines. So you've learned before that parallel lines are two lines that never intersect. Your job here is you're going to make parallel line segments, not lines, by connecting dots on here. So you got that idea of like two lines that aren't going to, there's really easy ways you could do this. See if you can think about it two different ways and make it a little bit more complex than that. So if I draw, if I draw this line segment and that line segment, are those parallel? Most likely you're going to say no, because eventually these two guys are going to crash into each other somewhere. Up here they're going to crash, big accident. Those aren't parallel lines because they're eventually going to intersect in some place. So see what you can do. It's one way to make it just horizontal or vertical. See if you can make parallel lines that are both diagonal in some way. The very next one says perpendicular lines. These are lines that intersect at a 90-degree angle. So I'm going to do one for you, just an easy one. You can see this right here. These are perpendicular lines because they do intersect right there at a 90-degree angle. If they go through, so there they were meeting, now they fully intersect and went through. I got to stop saying lines because those are line segments because they're not going on forever, they're stopping. Your next one's on there and make a right angle, make an obtuse angle, and make an acute angle. I'm not going to give the right angle because you know right angles off of this. An obtuse angle opens up greater than 90 degrees, or if we look at it as a circle, it's going to be more than 1/4 of a circle. And then an acute angle less than 90 degrees or less than 1/4 of the circle. So you're going to make two of those for every single, you're going to make two for every, you're going to give an example of two for every problem A through E. Let's move on to number 2. I'm going to get rid of you. So number 2 asks which expression shows one way to find the perimeter of a rectangle. I'm going to choose a different rectangle, and we're going to see how many different expressions that we can come up with to find the perimeter of this rectangle. I'm going to make it 12 inches by 6 inches. Just pretend those are right angles. So what is one way that we could find the perimeter? Perimeter being the one-dimensional length all the way around the outside of the rectangle. So a lot of times you said, I add for perimeter. So I could do 12 inches plus 6 inches. And that would be just from there to there to there. And now I need to go back over here. So that's another 12 inches. And then from there to there, another 6 inches. I could add up all of those, that would give me the perimeter. But in this case, we're just writing expressions, meaning we're not worried about what it's equal to, even though it gives you equal on the your example. No, it did say equation, so I'm not going to answer it for you. So what's another expression that we could make? I think you've seen 2 times the length plus 2 times the width before. So what would that look like here? 2 times the length, 2 times 12 plus 2 times 6. And I'm not going to answer it for you. Is there another way we could do it that's going to give us the same thing? What if I added up this side and that side, or the length and the width? So I could do 12 plus 6. Do I see another 12 plus 6 up there? Over here. So I could do 2 times 12, or the sum of 12 plus 6. You do these, see if every one of these gives us the exact same perimeter in this case, and one-dimensional inches. All right, we're on to the last one for day number 1 in week 3. So it says, using the digits 1 through 9, at most 1 time each, fill in the boxes to make the product as close to 7,000 as possible. So it looks like this. And we want to make our answer, as close to 7,000 as possible. I'm going to look at this a different way. Let's go with and for my example, we're going to try to get as close to 5,000. So I have the digits 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to use an area model to try to see how close to 5,000 I can get. So if I start trying some numbers in here, let's say I do 23 times 47. So using an area model, I'm going to go, this is 20 plus 3, and then 40 plus 7. So all these different regions in there. So if I do 20 times 40, this region's 800. 20 times 7, this region is 140. If I do 40 times 3, I get 120. And 7 times 3 and 21. Just estimating right there, I'm nowhere close to 5,000. I have 800 plus 120 plus 140. I need something bigger. So let me try a little bit larger numbers. let's try, that was too small, so let's try 72 times 83. So I'm going to do 70 plus 2 times 80 plus 3. 80 times 70. Uh-oh, I got too big right away. So now I may want to back these numbers down. You're going to try the same thing. Maybe those numbers help you with yours to try to get as close to 7,000. But this idea of paying attention to the tens place and the place value, maybe using an area model to figure out what numbers make sense, might be a good strategy for you to go with. Everybody stay safe. This was the end of week 3, day 1.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Welcome back, 4th graders. It's Mr. Nick. We're ready for week 3, day number 2, mathematics. Your very first problem for day 1 says building a deck. Alexandra and her dad built a deck in their backyard. It had an area of 48 square feet and a perimeter of 28 feet. Circle the drawing that best shows the deck that they built. Use numbers, labeled sketches, and words to explain your answer. So I talked to Alexandra and her dad, and they also wanted to build a fence for their pet dog, just a little cage in their backyard. So they went to the store and they bought 30 feet of fence. So they have 30 feet of fence. They want to know what different ways they can make a little cage for their dog. So they have 30 feet, and they want to think about different ways they can make a fence. They're going to make it right in the middle of the yard. They're not backing it up to their house or anything. So one way they can make their fence would be 1 foot by, how many feet? If they had 1 foot here, they'd have 1 foot there. How long would this have to be? 14 feet. So for their little dog, how much space does their dog now have to play in if they built their fence at their 30 feet of fence? There's 14, 14, 28, 29, 30. How many square feet does their dog have to play in right now? 14 times 1, 14 square feet. That's not a lot of room for their dog. Is there another way that they could build their fence? Could they, what if they made it 2 feet wide? Would their area stay the same, or would it be different? So if it was 2 feet there, and 2 feet there, now they had 30 feet, 28, 26, 13 feet. 13 feet. So now their dog just got a whole bunch more room to play in, didn't it? Because now it is 13 by 26 square feet is a lot more than 14 square feet. But they still used 30 feet of fencing. Can we give their dog some more room? Because you probably want the dog to have as much space as possible. What other numbers could I use? What if I did 10 feet by 5 feet? There's 5 feet. Do I use up all 30 feet of fencing? 10, 20, 30. Now the dog has 50. Sorry, that was 26 square feet. 50 square feet of fencing. Or 50 square feet of area inside the fence. That's a whole lot more area for the dog to play in. See what you can do when you look at Alexandra and her dad's deck. See whatever deck they made, did they make the very most amount of area, space in their yard to sit on their deck with? Because there may be more than one way to do it with the 28 feet of perimeter that they did. Number 2 is a problem from a website called Brilliant. I'm going to tell you a little secret. Some of your teachers have called me whenever we use any problems from this website, and they say, Mr. Nick, I don't know how to do this one. So you guys are going to be able to figure this out better than them. I didn't give you, well, I'm going to show you how it's set up, and then we're going to do our own problem together down at the bottom. So anytime you see a red line, or in your case, a dotted line, that just means add them up. So 5 plus 9, those are red dotted lines, dashed line. All we have to do is add those up. So the question mark there equals 14. When you see solid lines, that means multiply. So 6 times some number equals 12. So in this case, the question mark equals 2. You have a different problem on the bottom. It looks similar to this, but you have 48. I made it with 36. So our job is, when I add up these 2 circles, and when I multiply this circle by this circle by this circle, it equals 36. So I want to think of what are 3 numbers using the number 3 that can be multiplied together to get 36. So what are ways I can make 36 using the number 3? So 3 times some number equals 36. So I could do 3 times 3 times 4. 3 times 4 is 12, times 3 is 36, or 9 times 4 is 36. So would that work all the way here? So if I put a 3 here, does 3 plus 4 equal, I'll write it on there really little. If I put 3 there, that will make a 7 there because I have to add those up. That doesn't work. If I put a 4 here, that would make that 8. 8 times 4 times 3 would not work. So I'm going to try a different number. How else could I possibly make it? In fact, I don't want to steal that opportunity. I think some of you have probably already figured out what numbers that I could use here. I don't want to steal that for you. This gives you 2 problems that you can be smarter than some of the teachers at. You could do it with 36, or you could do it with, and then do it on your own with number 48. So that's number 2 for day 1. That's number 2 for day 2. Number 3 for day 2 is count how many do you see here. So first off, what do you see there? There's a lot of shapes there. So I can say there's a lot of different things I can possibly count there. So if I wanted to count, this could be, I count one individual flower looking shape. I could also count, so I could say that's just one flower. I could also count, maybe I wanted to count how many individual shapes there are. So I could go, I'm going to start with the 2 green ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 shapes. And that's pretty easy. That's what we would do if we were in kindergarten. I want you to think about other things that 4th graders might count. So 4th graders might count, what is the perimeter if that distance there is 1 unit? What's the perimeter of this whole shape? Could you count the distance around the entire thing? If this shape was just made up of the blue rhombi or the rhombus, how many rhombi would it take to fill up the entire shape? If you were just to count it with the triangles, how many triangles would it take to fill up the entire shape? If you were to count what fraction of the entire shape is green, or what fraction is yellow, or what fraction is blue, how could you count that? That's it for day 2. We'll see you next time. Stay safe.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Hey, 4th graders and whoever else happens to be watching right now. We're on grade 4, week 3, day 3. So if your very first one, it says a fraction talk, and we have this arrow looking thing. Our job is to find out what fraction of this whole, if this is, the whole is 1 unit by 1 unit, so this whole square is the whole. Our job is to find out how much of the whole is shaded. So I want to see how precise we can get this without me doing anything for you. I want you to see what fractions that you do know. See if there's any fractions up here that you recognize, that you can see I can find that in there. So some fractions that you're familiar with. Most of us know what 1/2 looks like. We're pretty good with knowing what 1/4 looks like, maybe 1/3. And then in 4th grade, we got a lot of other fractions that we can work with. See if anywhere up here you can see where 1/2 is. If 1/2 was shaded, what would that look like? So ways that I can make 1/2. If I split it down the middle right there, and I were to shade all of that over here, that would be 1/2. It looks like this definitely not 1/2. It's not 1/2 over there. I see at least 2 1/4, maybe even 3 1/4 on here. But where I'm looking is not where it's shaded, it's where it's not shaded. See up here if you can see what I'm looking at. I even tell you, well, actually, if we look at it, you see a whole bunch of shapes up there. You see a bunch of different triangles. So, that are not shaded. Here's one triangle that's not shaded, one triangle that's not shaded, and another triangle that's not shaded. What fraction of that unshaded part, compared to the whole, what fraction is that unshaded part here, here, and here? And see if you can use that information to see how much of this whole shape, this 1 by 1 square, is shaded. Now I helped you a little bit more than I usually do, but I'm not going to take you all the way there. Using that information that I just gave you, I think you can figure out the answer. All right, we're on to number 2. Our job here is to see which one of these letters does not belong. Your job today is actually to find 2 different reasons for each letter why each one of those does not belong. So here's the questions I want you to ask yourself. Think about the geometric things that we've worked on through the weeks. We've worked on parallel, we've worked on perpendicular, we've worked on acute angles. We worked on obtuse angles. We worked on right angles. See if you see any of those in some of these shapes and not other ones of those shapes. So those are the geometric ideas that we've seen within there. Think about if you see any shapes inside there. We work with triangles and rhombuses or rhombi, and we work with parallelograms, circles, squares, rectangles. See if you see any of those inside there. We've worked on straight line and curved lines. Use that information to try to find 2 different reasons why each one of these may not belong. And that's just looking at geometry. Think about it with numbers. What are things that we could count inside of each one of these? Are some of those the same number if you were to count them? Is there one that's different if you were to count them? A lot of different ways you can look at this to try to figure out which one doesn't belong, or you can have some fun reasons, like when I was in school, A never belonged because I never got one of those on one of my pieces of paper that I got back to me. Have some fun with it, all right? See what you can do. Ask your brothers and sisters, ask your mom, ask your dad, ask your dog, which one of these doesn't belong. And our last one for today is to look at a visual pattern. We've done these before, and this is stage 1 or step 1, stage 2 or step 2, stage 3 or step 3, and your job is to see what stage 4 might look like. To figure that out, we're going to look at what do we see that always stays the same and what changes each step. So as I look at this right here, things that I see that are staying the same every single time. I see these 3 right here. There's 3 there. There's 3 there. There's 3 there. So stage 1, stage 2, stage 3. Those 3 are staying the same in every single one. That might not be the only thing that you see that's staying the same. Maybe you see this whole pattern there, and you see it again right there. Do you see it again in this one? You see that pattern again. So maybe that's what's staying the same each time for you. Now what's changing each time? So in this case, nothing, well, wait, it grew 1 up there and 2 down there. And the next time, it went 2 up and 2 down. So what might that look like as we move on to step 4? Other things do you see any things that we use to help us with our multiplication? So in stage 1, what happens if I move this guy from the top to right there? What would that look like for stage 2? So throughout these weeks, we looked at more efficient ways to count. So counting 1 at a time is not really that efficient. But by looking at patterns and saying, oh, if I move that there, what happens when I move there or there? Is there a more efficient way to count by looking at these patterns and these different arrays as I move from first to second to stage 3? That's it for day 3 of week 3. I'm Mr. Nick. We'll see you again soon.
Yeah, that's IPS.
What's going on?
I don't know.
Okay, try it now.
Yeah, that's IPS.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Good morning, IPS students. Good to see you again. This is Mr. Schnepp back with you again, and we're going to be working on some 5th grade math today. All right, we're going to start out today with fractions of wholes. And what I have drawn up here on the board is we're going to look for 3/4 of 6. So if you look here, we've got 6 wholes. Okay, but we're looking for the 3/4 of 6. So I want you to think in your head And shout out to whoever's in the room there, what do we need to divide each of these holes into? Take a second to think about that. And if you said 3/4 or fourths, you're correct. So we're going to divide each of these 6 holes into fourths. Okay, so now we have our 6 holes, so that the block represents a hole, and then each of these represent 1/4. All right, so we're looking for 3/4 of 6. So what we need to do is we need to go through and we need to shade in 3/4 of each square. So what we have drawn here is 3/4 of 6. Each square has 3/4. So let's go count how many fourths we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have 18 fourths represented here. All right, so this is a number larger than 1 or a mixed number, but we need it simplified with how many fourths do we actually have. Okay, and if you remember in past lessons, one way we talked about that is we take the fraction, put the top number on the inside and the bottom number on the outside, and we divide it. So 4 goes into 18 4 times. 4 times 4 is 16 with 2 left over. And that gives us 4 2/2. Okay, and we could actually 4 2/4, and we could actually simplify that to 4 1/2. Okay, so that's a visual model of 3/4 of 6. Okay, I want to do the algorithm part of it, and we've talked before. We know that of means multiply. Okay, so we're going to change this problem. We'll rewrite it as 3/4 times 6. Same thing that we have here. That we have demonstrated here. Now, if you remember, how do you write 6 as a fraction? Every number can be written as a fraction. So think about that. Tell someone there in the room with you or what you think the denominator should be. And the way that we write 6 as a fraction is we write it as 6/1. Because remember, we've talked about fractions are the same as division problems. So 6 divided by 1 equals 6. So we write it over 1. So then we just multiply across. 18/4. And if we simplify it, we come up with 4 1/2. So that's just a quick review of fractions of wholes. Okay, this is the visual model of what you see, because we have 18 fourths here, which is what we got there. And this is how you do the standard algorithm. Okay, for today's lesson, it's going to give you some different fractions, and it's going to ask you, so for example, 2/3 times 8 equals 15 1/3. Is that true or false? Okay, so the way that we're going to do that is we just solve the problem. 2/3 times 8/1. We multiply and we get 16/3. Okay, and then we simplify it. 3 goes into 16 5 times. 5 times, or I'm sorry, we put our 5 here. Okay, 5 times 3 is 15. The 1 is our numerator, and there's our denominator. So does 2/3 times 8 equal 15/3? True or false? The answer is false, because it's actually 5/3, not 15/3. So you would just circle that. All right, let's take a look at one other problem. And this one is 12 times 3/4 equals 9. Okay, so let's do the same thing. 12 over 1 times 3 over 4. 12 times 3 is 36. 1 times 4 is 4. 36 divided by 4 equals 9. So in this case, that would be true. 12 and 3/4 would be true. Okay, the next thing that we're going to do today is we're going to talk about multiplying fractions. You're going to be able to use the digits 1 through 9, like we've done before, one time each. And we're going to multiply a fraction times a fraction to get a fraction with a mixed number. Okay, so we're going to have to think about this a little bit, and so I'm going to go through a couple of examples. First off, let's try the fraction 4/5 times 7/8. Okay, so we're just going to multiply across. 4 times 7 is 28. 5 times 8 is 40. Can I turn this one into a mixed number? Look at the numerator and make a decision. Our numerator is less than the denominator, so no, we can't turn that into a mixed number. So when you're working this problem, can you multiply two fractions less than 1 to get a mixed number? And if you said the answer is no, you're correct. So that you do not want to do a fraction where the numerators are less than the denominator. Let's try. Let's look at it at a different way here. Okay, let's try 2/3 times 6/5. Now we have a fraction less than 1, but we also have a fraction greater than 1. So I don't know. What do you think? Do you think this one will work? Let me erase our answer here. So 2 times 6 is 12. 3 times 5 is 15. No, wait a second. We have a fraction larger than 1, though. How come our answer is not bigger than 1? Okay. What you have to remember is, even though we do have a fraction greater than 1 here, this one is less than 1. So our answer is still going to be less than 1, so that's not going to work either. So what do you think? What types of fractions do you think that we're going to have to make this problem work? If you said two fractions larger than 1, you were right. So let's try this problem. 4/3 times 8/2. Okay, we multiply 4 times 8 and we get 32. We multiply 3 times 2 and we get 6. So now we have 32/6. I think we can make a mixed number out of this one. So we go through our process of our division. 6 goes into 30 5 times for 30. So there's our 5. We have 2 left over, and our numerator is 6. So our answer as a mixed number is 5 2/6. Now, did we follow our rules? Did we use any number twice here? We have 2 2s here. So that one's not, it works, but in the context of doing our problem, we're going to have to come up with a different number. So that's your task. Your task is to try to find as large as a number as you can. That's a mixed number. All right, and use all these numbers once. So if your goal is to try to see if you can come up with a bigger number than this. So just as a reminder, the first part of our lesson was fractions as wholes, and you'll also find that again on day 4. There will be some other problems like that. That is our lesson for today. There's a couple other problems in your lesson that would be some problems that you can figure out, or puzzles that you can figure out. Have a great day and stay safe, and we will see you next time. Thank you.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Good morning, fifth graders. Mr. Schnepp from Christian Park Elementary back again with you today. Today we're going to talk about adding and subtracting fractions. You can see on our board here we have three different types of fractions, and we're going to start over here. And all of the fractions, as you notice, have different denominators. And we cannot add or subtract a fraction unless both of them have common denominators. Now there's two ways that we can find a common denominator. Okay, one way that we can find it is we can just take the bottom two numbers and multiply them together, and 5 times 8 would equal 40. Okay, this one would be a little bit different, all right, and we'll get to that in a second. And like this one, 5 times 2, 10 would be a common denominator. 8 times 3, 24 would be a common denominator. Another way that we can do it is we can find the least common multiple. So let's take 5 and 8 for example, all right. So we're going to take 5 and we're going to write down all the multiples of 5. So there's some multiples of 5, and then we're going to come down here and we're going to write multiples of 8. Okay, so here's some multiples of 5 and here's multiples of 8. So what I'm going to go down and look for is I'm going to look for the least common multiple. So I'm going to find a number up here and a number up here that are the same, but it's the smallest of all of them. So I go down through here and I see a 40 here and I see a 40 there. Okay, so that would be our least common multiple. So when I go to subtract 2 and 2/5 minus 3/8, I'm going to write, and I always like to do this vertically because it helps me just keep things lined up a little bit better. Okay, so there's our problem. And then we're going to use 40 as the least common multiple. Okay, so we're going to write an equivalent fraction for both of these that is equivalent to 40. Okay, so one of the things that I know that you've probably talked about this year is whatever you multiply the bottom number by, you multiply the top number by. So 5 times something equals 40. If I don't know off the top of my head, I can go through here and count 1, 2, 3, 4, 5, 6, 7, 8. So 5 times 8 equals 40. So 2 times 8 equals 16. Then I come down here, 8 times something equals 40. Well, I can go over here to my number line, 1, 2, 3, 4, 5. 8 times 5 is 40. So 3 times 5 equals 15. So now remember, this is a subtraction problem, and it's very important that you pay attention to details because some problems are subtraction and some are addition. Okay, so I'm going to subtract 15 minus 16 is 1. And 2, and this, since there's not a number here, that's the same as 0. So the answer for this first problem is 2 and 1/40. Okay? Just find your least common multiple. That's the easiest way to do it. Now let's go ahead and try and give number 2 a shot now. There's 3 problems. You said, Mr. Schnepp, find the least, with 2 of them, it was easy. You find the least common multiple. What are we going to do with 3 numbers? Well, that's what I want to tell you. All right, same process. We find the least common multiple. So let's find multiples of 4. 4, 8, 12, 16, 20, 24, 28. And let's come down here to the number 6. 6, 12, 18, 24, 30, 36, and let's do the 3. 3, 6, 9, 12. I'm going to stop right there. I don't need to spend my time going all the way down to that area. Actually, I am, because I want to show you something. 12, 15, 18, 21, 24, 27. Okay, so now we go through here. There's a 12 here, a 12 here, and a 12 here. So let's circle those 12s. Can you see any other numbers that are common? We'll circle them in purple. We got 24, 24, and 24. So which multiple are we looking for? Are we looking for the least common multiple or a multiple that's higher? You could use either one of them, but I'm going to tell you what's going to happen. If you choose the 24, you're going to have to simplify a lot more. You'll be able to make your answer a lot simpler if you use the smallest number. Okay, so we're going to use 12. So once again, I'm going to do what I showed you before, and I'm going to stack my numbers vertically. All right, 12 is our common multiple. Okay, so 4 goes into 12 3 times, so we multiply this by 3, and we get 3. 6 goes into 12 2 times, multiply this by 2, and we get 2. 3 goes into 12 4 times, times 4, and that's 4/12. So now we just go through and we add our numerators. 3 plus 2 is 5, plus 4 is 9. So our answer is 9/12, and we can simplify that by dividing by 3, which would give us an answer of 3/4. Okay, so we added 3 numbers together. This is also a way that you can compare to see which fraction would be larger and which would be smaller too. Okay, so that's our three-step problem, or our 3-number problem. Then let's go to the last one. Now we've talked about orders of operations this year, and that's one of the things that you're going to have to do with this problem, is you're going to have to do orders of operations. And let's review orders of operations really quick. Okay, so the steps in the order of operation are parentheses, exponents, multiplication, and division, and then addition and subtraction. Okay, I wanted to go ahead and go through those steps just in case you come up with something later this week on that. But today we're going to focus on the parentheses and the addition and subtraction. And one thing I want to mention about multiplication and division and addition and subtraction, it doesn't matter which one. So if you're on addition and subtraction, you do them in order from left to right. You don't do like all the addition, then the subtraction. If it's subtraction, addition, addition, then you do subtraction, addition, addition. So whatever comes first, and you just work your way from left to right. Okay, so we got 2 fractions here, all right, and we got them in parentheses. So we're going to have to solve both of these parentheses before we can come up with our answer. All right, so on this side, we're going to have 4/5 minus 1/2, okay? And once again, we go through the least common multiple. 2, 4, 6, 8, 10, 12, 5, 10. I can stop right there, okay? Because I got 10 and 10, those are the least. Times 5 and 1/2, that's 5/10. Times 2, and that's 8. So 8 minus 5 is 3. So on this side, we have 3/10. Look at the fractions on the other side. What do you notice that's different about those two? Do we have to come up with a common multiple for those? 8 over 8, 8/8. What number does that simplify to? Remember, think of it as a division problem. 8 divided by 8 equals 1. Okay, so we could just make this 1 minus and 3/3. 3 divided by 3 is 1. We can make that 1 also. So what's 1 minus 1? That's 0. So 3/10 minus 0, our answer is going to be 3/10. Okay, the main part of this lesson is the adding and subtracting fractions. There's also going to be a couple other things on day 2 that you might come across with patterns and with just a puzzle with comparing fractions. So that's our lesson for today. I hope you have a good rest of the day, and we will see you next time.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Good morning, IPS fifth graders. Mr. Schnepp from Christian Park Elementary here with you again today. The first thing that we're going to do with today's lesson is we're going to try to solve this story problem. Antonio and Lenasia are reading books for their book report. Antonio's book is 96 pages and he has read 4/6 of the book. Lenasia's book is 80 pages and she's read 3/5 of the book. Who has read the most pages so far? The method that we're going to use today to figure this out is using the tape method. And we've talked about tape method before. All right, so what we're going to do is we'll start over here with Antonio. And I'm going to draw a tape. And that tape represents the whole book. The whole book is 96 pages. So our tape is going to be 96. Okay, that's 96 pages. All right, so he's read 4/6 of the book. So whoever you're with there in the room, talk about how many sections we have to divide this tape into. If you said 6, that would be correct. So I draw 5 lines. Because remember, to make the sections, you draw 1 less line than the number that you need for your denominator. Okay, and then let's look at Lenasia's book. Okay, remember that tape represents the whole book. All right, so what does this represent? This represents 80 pages, that's correct. All right, and how many parts do we need to break Lenasia's tape into? If you said 5ths, that is correct. Okay, so now we need to figure out what is 1/6 and what is 1/5. Okay, so I'll give you a second to think. The way that I do it, and it's probably the easiest way, is I'll just take my denominator and divide it by the total number of pages. So 6 divided by 96, 6 goes into 9 one time. That's 6, that's 3, bring down the 6. 6 goes into 36. So if 1/6 is 16 pages, so we're going to put 16 in every one of these boxes. So every 6th of the book is 16 pages. Now we're going to come over to Lenasia's and do the same thing. 80 pages, and we're going to divide by 5 this time because it's in 5ths. 5 goes into 36 times. Well, that's so. This will be really simple to be able to figure out who read the most, because both of their fractions end up being the same amount. Okay, so a 1/5 of 80 is 16. 1/6 of 96 is 16. And if you remember back to an earlier lesson that we did, we worked on doing where we had fractions of wholes. Remember seeing problems like this? Okay, that's what we did earlier. Okay, so now we need to figure out who read the most pages. All right, so we're going to erase the 1/6 and the 1/5 here now. So Antonio read 4/6. So what we're going to do is we're going to draw brackets around 4/6. Okay, 1, 2, 3, 4, 5, 6. Okay, there's the 6th, and we're using these 4 here. For Lenasia, hers was 3/5. All right. So now all I need to do now is I can do it 2 ways. I can add 16 plus 16 plus 16 plus 16, or I can multiply 16 times 4. All right. 16 times 4, that's 24. So that's 64. So Antonio has read 64 pages. Okay, so since I did multiplication here for Antonio, I'm going to do repeated addition for Lenasia. 16 plus 16 plus 16. 6 plus 6 plus 6 is 18. Carry the 1. 1, 2, 3, 4. That's 48 pages. So who has read the most pages so far? Antonio has. So when you have two things that you're trying to compare, making a tape diagram, all right, and the tape being the whole and dividing it into the proper fraction will make it a lot easier for you to figure out how many a percent or a fraction of a number. Okay, we're going to talk about comparing fractions for this lesson. And we did something similar to this earlier this week when we were adding fractions. I talked about finding the least common multiple. So when we compare fractions, we're also going to find the least common multiple for that. So we're looking for the LCM, which means least common multiple. Okay, and we're going to take numbers 6 and 24. So we're going to find the least common multiple of 6 and 24. So we're going to count the multiples of 6. 6, 12, 18, 24, 30, 36, and we'll stop at 42. Okay, now the multiples of 24. We have 24, 48, and I believe 72, then 96. Okay. So once again, we're looking for the least common multiple. So we go through here. Here's a 24. That's the smallest number. And I'll find a 24 here. So the least common multiple between 6 and 24 is 24. Let's look at the numbers 4 and 9. Okay, so let's list the multiples of 4. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48. And the multiples of 9. 9, 18, 27, 36, 45, 54, 63, 72. All right, so we can stop there. So we're going to find the least common multiple. We've got to do a little bit of work here. As I look up and down both of the numbers here, I see a 36 here and a 36 there. So the least common multiple of 4 and 9 is 36. Okay, so now we're going to apply that to a problem and compare two fractions together. All right, and the two fractions that we're going to compare, 6/8 and 17/28. Okay, 6/8 and 17/28. Okay, so what do we have to do first? We have to find common multiple. So let's look at 8. 8 times 1 is 8. 8 times 2 is 16. 8 times 3 is 24. 8 times 4 is 32. 8 times 5 is 40. 8 times 6 is 48. 8 times 7 is 56. 8 times 8 is 64. Okay, and then we're going to go down to the number 28. 28 times 2 is 56. 28 times 3 is 84. Okay, we can stop there because I remember saying 56 here. Okay, so the least common multiple is 56. Okay, so let's find an equivalent fraction to 6/8 that has 56 as the denominator. Because remember, in order to compare two fractions, our denominator has to be the same. Okay, 8 goes into 56, and if I can't remember what I multiply, what the facts are, I can just count 1, 2, 3, 4, 5, 6, 7. 8 times 7 equals 56. Multiply the top number by 7. 6 times 7 equals 42. So then we come over here with 17/28. Once again, 56 is our common denominator. All right, 28 goes into 56 twice. All right, 1, 2. So I multiply 17 by 2, and I get 34. Okay, so now in order to compare, I'm going to compare these two fractions. I'm going to look at these two fractions right here because the denominators are the same. 42 is larger than 34. So 6/8 is greater than 17/28. That's our lesson for today. I hope you guys enjoy the rest of your week, and I will see you back here next week to work on week 4. Thank you.
That's IPS.
You're watching MyIPS on MyINDY-TV 23, a free educational service provided by Circle City Broadcasting of Indianapolis. Here's what's coming up this hour. Get more information, special announcements, and weekly program schedules online at wishtv.com. And be sure to follow us on Facebook. Here's what's coming up next.
My name is Mrs. Meadows. I've been teaching mathematics for 17 years. Now I'm at Great Minds, and I'm looking forward to teaching you the lessons in this course. Remember to let your teachers know that you are participating in this program. Today we will be working on Grade 6, Module 4, Lesson 3. We will build and clarify the relationship between multiplication and addition by evaluating identities. You will need the following materials: a copy of your student page for our lesson today, or a piece of paper. You will also need a pencil. If you don't have any of these items, it's okay. You can just follow along with the lesson. Please pause the video while you gather your materials and resume it when you're ready. Okay, let's begin. For our opening exercise, we are going to write an addition expression and a multiplication expression for each. In this diagram, how many units are in each tape? 3. I want you to take a few seconds to think about how we write that as an addition expression. Three plus 3 plus 3. How many tapes do I have containing 3 units? 3. Take a moment to think about how I can write that as a multiplication expression. Three times 3. Since both expressions are presented by the same diagram, can we say that the expressions have the same value? Let's try another one. In this diagram, how many units are in each tape? 8. How can you write that as an addition expression? 8 plus 8. Now think about how many tapes do I have containing 8 units? 2. How can I write that as a multiplication expression? 2 times 8. Since both expressions, 8 plus 8 and 2 times 8, are represented by the same diagram, can these two expressions be equivalent? Let's try one more. In this diagram, how many units are in each tape? 5. How can I write that as an addition expression? Five plus 5 plus 5. How can I write that now as a multiplication expression? Three times 5. Since both expressions are represented by the same diagram, can we say that 5 plus 5 plus 5 and 3 times 5 have the same value? Let's go ahead and review. 3 plus 3 plus 3, 3 times 3, 8 plus 8, 2 times 8, and 5 plus 5 plus 5 and 3 times 5. Take a look at the expressions that we created. If both expressions yield the same value, is there an advantage to using one over the other? Oh, I wish I could hear all of your responses, but I want you to hold your thoughts because we're going to come back to this question at the very end of the lesson. Now, let's create an equation from a tape diagram that models the relationship between multiplication and addition as we see here. First, I want you to choose a variable. It doesn't matter what you choose. You can choose your favorite letter from the alphabet. I'm going to choose G. My G will represent the same number. How can I write an addition expression from this tape diagram? G plus G plus G. How can I write a multiplication expression from this tape diagram? Three G. Did you notice anything about the way that I've written my equation? Earlier, we wrote our expressions with the multiplication symbol. 3G is the same as writing 3 times G, but we're no longer going to use the X for multiplication. Why? Because it looks like a variable and it can get really confusing. So when you see the number 3 or any number next to a variable, that means multiplication. In the first two lessons, we talked about identities. Take a moment to think about, is the equation 3G equals G plus G plus G an identity? It is an identity because we can replace G with any number and the equation will always be true. I know what you're thinking. Go ahead and pause the video, plug in whatever numbers you want to, and see if you can prove me wrong. I'll be here when you get back. So, did you prove me wrong? Excellent. It will always be true, no matter what value you substitute in for G. Let's begin our exercises. Write an addition sentence that describes the model and the multiplication sentence that describes the model. Five plus 5 plus 5 is an addition expression, and 3 times 5 is a multiplication expression that represents this model. Now I'm going to pause the video Hi, my name is Mrs. Meadows. I've been teaching mathematics for 17 years. Now I'm at Great Minds and I'm looking forward to teaching you the lessons in this course. Remember to let your teachers know that you are participating in this program. Today we will cover Grade 6, Module 4, Lesson 4. If you have your workbook at home, your page should look like this. If you don't have your workbook, that's okay. Just grab a piece of paper and a pencil. In this lesson, we will create tape diagrams. So you can use square tiles. You can cut identical squares from a piece of paper. Or you can use sticky notes. Okay, let's begin. The first thing we're going to do is build a tape diagram with 20 squares. You can use whatever materials you prefer to build your tape diagram. You can pause the video at this time. Next, we're going to divide our tape diagram into 4 equal parts. How many squares are in each of the 4 sections? That's right, 5. Squares are in each section. Take a moment to write a number sentence to model what we just displayed with our tape diagram. Our number sentence will be 20 divided by 4 equals 5. Now let's combine our squares again to have a tape diagram of 20 squares. Now let's subtract 4 squares from our tape diagram. Let's write an expression to model what we just did. 20 minus 4. We had 20 squares and subtracted how many? 4. Excellent. Let's do it again. Subtract another 4 squares. Now let's alter our expression to reflect what we just did with our square tiles. 20 minus 4 minus 4. Now let's subtract another 4 square tiles. Let's alter our expression to reflect what we just modeled. 20 minus 4 minus 4 minus 4. Now let's take away another 4 square tiles. Let's alter our expression again to reflect what we just modeled. 20 minus 4 minus 4 minus 4 minus 4. Now let's take away our last 4 square tiles. How many are we left with? 0. Good. Let's alter our expression to reflect what we just did with our square tiles. 20 minus 4 minus 4 minus 4 minus 4 minus 4 equals 0. Now let's take a look at the process we used to get to 0. How many times did we subtract 4 to get to 0? 20 minus 4 equals 16. 16 minus 4 equals 12. 12 minus 4 equals 8. 8 minus 4 equals 4. And 4 minus 4 equals 0. Notice we subtracted 4 5 times. The quotient is 5. Now let's look at a similar problem. 20 divided by 5 equals 4. To see if the quotient is the number of times the divisor is subtracted from the dividend, in order to do that, why don't we create a number sentence where we will subtract the divisor? 20 minus 5 minus 5 minus 5 minus 5 equals 0. Now, let's take a moment to look at the process we use to get to 0. How many times did we subtract 5 to get to 0? 4. Notice that we subtracted 5 4 times. That tells us that the quotient is 4. 20 minus 5 equals 15. 15 minus 5 equals 10. 10 minus 5 equals 5. And 5 minus 5 equals 0. We subtracted 4 times. What do you notice about the relationship between 20 divided by 5 equals 4 and 20 minus 5 minus 5 minus 5 minus 5 equals 0? "20 divided by 5 equals 4 can be interpreted as subtracting 4 fives from 20, which will equal 0. Is that relationship always true? Well, let's try to prove this. So x represents a number. What does 12 divided by x equals 4 mean? Well, let's start by creating a subtraction expression when each x is subtracted. Here, we see that exactly 4 x's can be subtracted from 20. What must x be in this division sentence? Five. What two operations are we relating in the problems we completed? Division and subtraction. Now we'll take a look at exercise 1. Pause the video and take as much time as you need. I will be here when you get back. Let's review our answers. Now let's take a look at exercise 2. Pause the video and take as much time as you need. We will review the answers when you're ready. In each of the circles, we can place an operation to satisfy this organizer. In the last 4 lessons, we have discovered that each operation has a relationship with other operations, whether they are inverse operations or they are repeats of another. What is the inverse operation of addition? Subtraction. After our discussion today, repeated subtraction can be represented by what operation? Division. Which operation is the inverse of addition? Multiplication. Let's see if this is correct. Is multiplication the repeated operation of addition? Yes. Understanding the relationships of operations is going to be instrumental when solving equations later in this unit. That's it for today. I'm Mrs. Meadows, and remember to let your teachers know you are hard at work with this course, and I hope to see you tomorrow. Hi, my name is Mrs. Meadows. I've been teaching mathematics for 17 years. Now I'm at Great Minds, and I'm looking forward to teaching you the lessons in this course. Remember to let your teachers know that you are participating in this program. Today we will cover Grade 6, Module 4, Lesson 4. If you have your workbook at home, your page should look like this. If you don't have your workbook, that's okay. Just grab a piece of paper and a pencil. In this lesson, we will create tape diagrams. So you can use square tiles. You can cut identical squares from a piece of paper, or you can use sticky notes. Okay, let's begin. The first thing we're going to do is build a tape diagram with 20 squares. You can use whatever materials you prefer to build your tape diagram. You can pause the video at this time. Next, we're going to divide our tape diagram into 4 equal parts. How many squares are in each of the 4 sections? That's right, 5. Squares are in each section. Take a moment to write a number sentence to model what we just displayed with our tape diagram. Our number sentence will be 20 divided by 4 equals 5. Now let's combine our squares again to have a tape diagram of 20 squares. Now let's subtract 4 squares from our tape diagram. Let's write an expression to model what we just did. 20 minus 4. We had 20 squares and subtracted how many? 4. Excellent. Let's do it again. Subtract another 4 squares. Now let's alter our expression to reflect what we just did with our square tiles. 20 minus 4 minus 4. Now let's subtract another 4 square tiles. Let's alter our expression to reflect what we just modeled. 20 minus 4 minus 4 minus 4. Now let's take away another 4 square tiles. Let's alter our expression again to reflect what we just modeled. 20 minus 4 minus 4 minus 4 minus 4. Now let's take away our last 4 square tiles. How many are we left with? 0. Good. Let's alter our expression to reflect what we just did with our square tiles. 20 minus 4 minus 4 minus 4 minus 4 minus 4 equals 0. Now let's take a look at the process we used to get to 0. How many times did we subtract 4 to get to 0? (20 minus 4 equals 16). 16 minus 4 equals 12. 12 minus 4 equals 8. 8 minus 4 equals 4. And 4 minus 4 equals 0. Notice we subtracted 4 5 times. The quotient is 5. Now let's look at a similar problem. 20 divided by 5 equals 4. To see if the quotient is the number of times the divisor is subtracted from the dividend, in order to do that, why don't we create a number sentence where we will subtract the divisor? 20 minus 5 minus 5 minus 5 minus 5 equals 0. Now, let's take a moment to look at the process we used to get to 0. How many times did we subtract 5 to get to 0? 4. Notice that we subtracted 5 4 times. That tells us that the quotient is 4. 20 minus 5 equals 15. 15 minus 5 equals 10. 10 minus 5 equals 5. And 5 minus 5 equals 0. We subtracted 4 times. What do you notice about the relationship between 20 divided by 5 equals 4 and 20 minus 5 minus 5 minus 5 minus 5 equals 0? (20 divided by 5 equals 4 can be interpreted as subtracting 4 5s from 20, which will equal 0. Is that relationship always true? Well, let's try to prove this. So x represents a number. What does 12 divided by x equals 4 mean? Well, let's start by creating a subtraction expression when each x is subtracted. Here, we see that exactly 4 x's can be subtracted from 20. What must x be in this division sentence? Five. What two operations are we relating in the problems we completed? Division and subtraction. Now we'll take a look at exercise 1. Pause the video and take as much time as you need. I will be here when you get back. Let's review our answers. Now let's take a look at exercise 2. Pause the video and take as much time as you need. We will review the answers when you're ready. In each of the circles, we can place an operation to satisfy this organizer. In the last 4 lessons, we have discovered that each operation has a relationship with other operations, whether they are inverse operations or they are repeats of another. What is the inverse operation of addition? Subtraction. After our discussion today, repeated subtraction can be represented by what operation? Division. Which operation is the inverse of addition? Multiplication. Let's see if this is correct. Is multiplication the repeated operation of addition? Yes. Understanding the relationships of operations is going to be instrumental when solving equations later in this unit. That's it for today. I'm Mrs. Meadows, and remember to let your teachers know you are hard at work with this course, and I hope to see you tomorrow.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
All right, hello guys, this is Mrs. Couch and I'm going to be working on 7th grade math with you again. Today we're going to be doing Unit 6, Lesson 5, Reasoning about Equations and Tape Diagrams. I hope you were able to view the previous lessons and you have an idea of what tape diagrams look like. But if you don't, you're going to get a little bit of exposure to it today, so don't worry. All right, so 5.1, it says Algebra Talk, Seeing Structure. It asks us to solve each of these equations mentally. So that's hard for me to do, and to show you my thinking, I am going to draw on the board, so don't judge me. But I'm going to think about it before I do. So when we think about tape diagrams, I like to think of them as puzzles. And so we have this first math sentence. We have x minus 1 equals 5. All right, so 5 is going to be our whole puzzle all together. So in this case, it'll just be a nice little rectangle. And then these are our pieces that go into our puzzle. So we don't know what x is, but we do know that we're going to be subtracting 1 in order to make the 5. We have 5 here. All right, so we have x, and when we subtract that 1, we have a 5 total. And so you notice that I made that a -1, right? And this is actually just like adding a -1 value, okay? And so if I put it in a tape diagram, I want to show that as a negative number, because what it's actually going to do is it's going to cut into that x in order to make the 5. Does that make sense? All right, so when we think about this one, it is a little bit different because we have these parentheses here, meaning that we're multiplying that 2 by this whole quantity, okay? Our whole this time is going to be 10, okay? And since we have 2 of equal value being multiplied together, we're going to just split it in half, and then we're going to have an x minus 1 on one side, and x minus 1 on the other, okay? Moving on, I can do this one over here. So we have 3 times x minus 1, the quantity. That means that we're going to have 3 of these pieces in order to equal this 15. So how many equals pieces am I going to need in this rectangle? That's right, I'm going to need 3 because I have 3 of this quantity. So I have 1 here and 1 here. And if your picture is not exactly equal, it doesn't really matter at this point because we're just trying to understand. We just need to know that these are the same value. And then that equals 15. All right, so then we have this one, which is really interesting. We have 500, the total. So I'm going to go ahead and write my whole. And it doesn't matter the size of the rectangle, right? I could have a rectangle this small, and I could say it equals 500, and I could say this equals 500 because I created it. But for the sake of my handwriting, I'm going to make it a little bit bigger. All right, so this 500 is equal to 100 x minus 1s. So 100 of these guys. So do I want to do 100 boxes in here? No, not really. So what I'm going to do first is I'm going to distribute this 100. So I have 100x, and then what we're actually doing is we're subtracting 100 or adding negative 100. Okay, these are saying the same thing. We're just taking that value away 2 different ways. So if that's the case, that means I can split it up and I can put 100x, and then I will put the negative 100 over here. And then that way, I don't have to write 100 little boxes like I did here. I just have these 2 boxes representing this new equation, but it's the same math sentence. Isn't that interesting? All right, so we're going to utilize this information and these tape diagrams in order to help us move through 5.2. I'm going to help you set up your tape diagrams, and you're going to solve them on your own. 5.2, guys. So the first problem reads, each of 5 gift bags contains X pencils. There's our variable. We already have it given to us, X pencils, the unknown. And Tyler adds 3 more pencils to each bag. Altogether, the gift bags contain 20 pencils. So I am helping you draw the tape diagram only. You guys are going to be expected to write the equation that represents this picture and solve for the unknown. So just remember that. Don't forget to do it. Okay, so what is the whole in our situation? Right, the 20 pencils all together, right? That word all together means a whole, everybody all in one group. So that is our key word to know. That is our whole number of 20. Okay, and so then we need, I like to work backwards. So Tyler adds 3 more pencils to each bag, and then each of 5 gift bags contains X pencils. So I have 5 gift bags, and they're all going to have the same thing in them, so they're going to be equal in value. So I'm going to try and make this as equal as I can. 1, 2, 3, 4, 5. Not bad. All right, so within those bags, I have X pencils. And then he adds 3 more pencils to each bag. So X plus 3. All right, so how many of the quantity X plus 3 do we have? 1, 2, 3, 4, 5, right? And then that is equal to 20. Utilize this tape diagram, write it down on your paper to help you solve the problem on your own. Now we're going to move on to number 2. Number 2 reads that Noah drew an equilateral triangle, which means that all sides are the same length, and the sides have a length of 5 inches. He wants to increase the length of each side by X inches so the triangle is still equilateral, means equal on all sides, and has a perimeter of 20 inches. So the perimeter is adding all those edges together. So for this one, I do want to draw a picture just because it's a little different than what we've been experiencing so far. So I'm going to draw these lines here. This notes that each of these sides are equal to the other, and we're going to say that originally these were 5 inches, okay? And so the story goes is that he wants to increase, which means add, the length of each side by X inches. This is our unknown. And then that means that the triangle will still have to be equilateral and have a perimeter of 20 inches, okay? And so the perimeter is side 1, side 2, side 3, all added together. So each of these is going to have this 5 plus X here, okay? So we have 5 plus X on this side, then we have 5 plus X on this side, and 5 plus X on this side. So our tape diagram is going to have 3 equal squares. And they are going to have our one-side equation in each of them. And then that is going to equal our total, our whole of 20, okay? So I would at least write the tape diagram down in order to help you solve number 2. All right, so I'm going to quickly erase these 2, and then I'm going to work on 3 and 4 with you, and then you will do 5.3 on your own. All right, so we're still on 5.2, but we're at number 3 now. Number 3 reads that an art class charges each student $3 to attend plus a fee for supplies. Today, $20 was collected for the students attending the class. So first off, I want to think about which one has our unknown, because for some situations, we have to decide the variable on our own. And I didn't see a variable in here given to us. So let's go ahead and try and draw the tape diagram and see where our missing pieces are. So if you look backwards, it says today $20 was collected from the 5 students attending the class. So that gives me 2 pieces of information. It gives me my total of $20. And then it gives me how many equal spaces we need. We need 5 for each kid. 1, 2, 3, 4, and 5. All right. So then the art class charges already $3 for each student. So that's something we know. And then it says $3 charge plus a fee for supplies. Now we don't know how much that fee is, so I'm actually going to represent it with an F, and that's going to stand for the unknown fee that we have, and we're going to add that F to each student. All right, you can use any letter you want, but I like to use numbers that are relative to the story to help me remember the context. So this F is going to represent the fee, and you can utilize this to solve your problem for number 3. Now number 4, I had to think about this one for a bit. So Elena ran 20 miles this week, which was 3 times as far as Claire ran this week. Claire ran 5 more miles this week than she did last week. So I had to think about this for a little bit because I was trying to think, what are they wanting us to answer? What is the unknown, right? And so if we look back, we do know our total, which is the amount that Elena ran, which is 20 miles. Go ahead and label that. And we know that that was 3 times as far as Claire ran this week. So I'm going to need 3 boxes because it's 3 times the same value that Claire ran. All right. And if this is going over your head, feel free to just keep listening to me as I move along. And if you have any more questions, please reach out to your teacher for some extra help. All right, and so now we need to think what goes in these boxes. So we know one more number. It says Claire ran 5 more miles this week than she did last week. But what we don't know is how much she ran last week. And so that is our unknown. And I'm just going to make an X this time. I'm going to make X represent the miles that Claire ran last week. Okay, and so if it's 5 more, that means additional, which means we're going to be adding the 2 together. So we have X plus 5, X plus 5, and X plus 5. All right, so for 3 and 4, here are your tape diagrams. Please write them down, take a moment, pause the show, and utilize this information to help you solve, because you're not done with this one until you solve it and find that missing variable. All right, so 5.3 is going to include the information from 5.2. It says each situation in the previous activity is represented by one of the equations below. You have 2 equations down there. X plus 3, the quantity, times 5 equals 20, and 3 times the quantity, x plus 5 equals 20. You're supposed to match each situation to an equation, find the solution, and use the diagrams, and then what does each solution, tell you about its situation. All right, so do your best, ask questions, and remember that we're here for you if you need us. All right, I will see you next time for our next lesson, Unit 6, Lesson 6.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
All right, guys, thanks for coming back with me, and thanks to all the new people who are coming to visit and learn some math with me today. We are doing Grade 7 Math, Unit 6, Lesson 6, and we're going to be working on distinguishing between 2 types of situations. Now, that is a very vague thing, but I will tell you that it's going to deal with tape diagrams and looking at equations utilizing that. So let's look at 6.1. We're asked which one doesn't belong. So we have 4 equations. This first one is 4 times the quantity x plus 3, and that's equal to 9. We have 4 times x plus 12, which equals 9. We have 4 plus 3x equaling 9, and then we have 9 equaling 12 plus 4x. So when you glance at it, they all have a lot of similar numbers, no crazy variables. We're all basically adding. So it's kind of hard to tell by just glancing at them which one is different and which one doesn't belong with the rest. So I'm going to use our prior knowledge and draw some tape diagrams to help me see these a little more clearly. So I'm going to draw my diagram. I have my whole of 9, and then I have 4 squares, or 4 pieces, sorry, and they all have x plus 3 in them. All right, now let's look at this next one. We have our total of 9. So, and then that is going to equal 4 x's, right? Because we have the 4 times the x, which could also be written like this. So that means that we're going to have 1, 2, 3, 4. X, 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 and then what is left over, we're going to be adding that 12 in. So let's look at this next one. I'm going to draw it over here for some extra space. We have our 9 as our total still, so far we're pretty similar. We have 3 x's this time, and then we're going to be adding a 4. So 4 is a little less than halfway, so I'm going to be adding that, and then 3 X's. Okay, and then I have this final one down here. Same whole value of 9. And then we have our 4 X's here, and then we have the 12 again. So let's do 12, and then 4 X's. Okay, so when we draw this out, does it help us see some similarities, some patterns, maybe some things that stick out? All right, good, because there are definitely some things that are sticking out. So you see this guy right here? We have the 12, and then we have the 4 X's. It doesn't matter the order, right, because they're all being added together. So these guys are similar. So then we have to determine which one looks like these two, because only one of them doesn't belong. So one of these has to fit in with these. So let's think about this. X, 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 4. Could that turn into anything else? No, we can't do anything with this. It just is what it is. We could make it 3x maybe, but that doesn't make it 4 x's, and the 4 can't magically change into a 12. Let's look at this one. So we have x plus 3, x plus 3, x plus 3, x plus 3. But just like we did in a previous problem, instead of leaving them in their quantities, I actually can distribute the problem and make the picture look a little bit different. So if I distributed this out, I would actually get 4x, and then I would add my 12, which should sound very familiar to our other two problems, and it can be written the same way. 1, 2, 3, 4 x's plus a 12 equaling the whole of 9. So this one is equal to this one, which is equal to this one, which is equal to this one, meaning that these three are all alike, and this one is the one that doesn't belong. Isn't that interesting? Utilizing this visual helps us understand the problems from, I think, a deeper perspective. So I really like to utilize them as a tool moving forward. And in 6.2, we're going to be utilizing them some more to talk about two stories and comparing them. So go ahead and hang on with me, and I'll be right back with a clean board ready to go. All right, guys, so 6.2, it looks like we have two tape diagrams here. I went ahead and drew them on the board just to help me out. Number 1 says which diagram goes with which story, and be prepared to explain your reasoning. So I'm going to read both stories, and then we're going to think about them for a second and see which one matches which visual representation. So story number 1 says Lynn had 90 flyers to hang up around the school. She gave 12 flyers to each of 3 volunteers. Then she took the remaining flyers and divided them up equally between 3 volunteers. All right, that's the end of story number 1. Here's story number 2. Lynn had 90 flyers to hang up around the school. After giving the same number of flyers to each 3 volunteers, she had 12 left to hang up by herself. All right, so both stories involve Lynn handing out 90 flyers, but the way they were distributed is a little different. So if we look at this first story, it says she gave 12 flyers to each of 3 volunteers. All right, so does this one have 3 12s? No. So I kind of already know that this is the direction I'm heading, but we will read through it some more just to double check. So then she took the remaining flyers, which are an unknown amount, and then divided them up equally between the 3 volunteers. Again, 3 spaces, 3 Ys, 3 unknowns added to the 12, added to the 3 boxes. So that being evenly distributed, it doesn't really look like this is very evenly distributed. We have 3 values that are the same here, but then we have a 12 here. So this one isn't as even, whereas this is equal in its distribution, and so therefore story 1 goes with B. And, you know, deductive reasoning states that if 1 is B, then 2 is A, because we only have one other option, but let's talk about it a little. So Lynn had her whole 90 flyers. After giving the same number of flyers to each volunteer, which we don't know how much that is, she had 12 left to hang up by herself. So here is the 12 that Lynn had to hang up by herself, and then here are the 3 unknown but equal values represented right here. All right, so number 2 says, in each diagram, what part of the story does the variable represent? So we did talk about this a little bit. So for A, let's think about what x equals, right, or means. What are we looking for? Unknown. So she took the remaining flyers and divided them up equally between 3 volunteers. Well, the remaining flyers, we don't know exactly what number that is, so that's our unknown, that's our variable. So x equals the flyers given per volunteer. All right, let's think about B. B's variable is y. And the story states that after giving the same number of flyers to each 3 volunteers, she had, I did this backwards. I mean, they're both the flyers given to the volunteers, but I did them backwards, so excuse me. All right, so A states that she took the remaining flyers and divided them up equally between 3 volunteers, so that X is that remaining flyers that was divided equally. I did it again. I'm wrong again. So, because I keep thinking in the stories. So let's do it like this. Story 1 and story 2. So story 2 is represented by B, and story 1 is represented by A. So hopefully that'll help keep my brain organized. All right, so story 1, we have the unknown variable of y. So let's look at story B. So story B that states that after giving the same number of flyers to each 3 volunteers, she had 12 left to hang up by herself. So that y represents the flyers that she gave out first to the volunteers. So flyers given to volunteers. Story number 2 is represented by visual A. And story number 2 states that after giving the same number of flyers to each 3 volunteers, which that is our unknown, that's our X, she had 12 left to hang up by herself. So that X equals the remaining flyers. I know, guys, it's not as smooth as normal, but I will get through it. All right. So number 3 says write an equation corresponding to each story, and if you get stuck, use the diagram. And then number 5 says find the value of the variable in the story. So you guys can do 3 and 4 on your own because I believe in you, and I know that we've talked about tape diagrams probably about as much as I can. So I know that if you've been watching this, that you probably have a good idea of tape diagrams as well. So utilize your understanding to help you solve the rest of 6.2 and try and challenge yourself with the challenge on the back that says, are you ready for more? All right, so keep growing, keep trying, and keep reaching out to your teachers for help. We're here for you, we miss you, and we can't wait to see you again. Take care, be safe, and have a good day.
What's going on?
I don't know.
Okay, try it now.
Yeah, that's IPS.
Look around. Listen. We're moving to a new beat. A colorful symphony, each note made more beautiful by the next. We are driven by talent in the classroom, in each school that recognizes the potential in every student and knows the opportunity to achieve is not an option, it's expected. We are not alone. We stand among giants, eager to help, eager to give back and build bonds to last generations. We are part of a city fueled by grit, strength, and determination. Racing toward a future full of potential where hard work really does pay off. When one succeeds, we all succeed. We're innovative. We're industrious. We're imaginative. We are your Indianapolis Public Schools, and we're stronger together.